Good morning to one and all. I would like to start our today's webinar with a quote: "By failing to prepare, you are preparing to fail," by Benjamin Franklin. I welcome and thank you all for joining us today for this webinar on overview of VLSI industry fundings and career opportunities. Now I request Professor Navya Holla K to introduce today's speaker, Mr. Shivappa KM, on overview of VLSI industry fundings and career opportunities. Navya, you can start.
Good morning, everyone. This is Navya Holla, Assistant Professor from ECE Department, DSE. Today, we are pleased to welcome Mr. Shivappa KM, a very special guest from Excel VLSI Technologies, Bangalore. Mr. Shivappa is a COE and co-founder of Excel VLSI Technologies Private Limited with immense experience in the IT service industry and education. Majority in ASIC with great insight into dynamic trends and latest technologies in the semiconductor industry. He has over 2 decades of work experience in prominent companies such as Wipro, Mindtree, SmartPlay, and Arisent. His expertise lies in ASIC design verification methodologies and has extensive protocol knowledge. He has published several technical papers in design verification forums. And today he will be sharing with us his expert opinion on overview of VLSI industry fundings and career opportunities. With that, I request you to give your full attention to our speaker and help us in welcoming him to this webinar. Sir, once again, I welcome and thank you for being with us. Thank you.
Thank you, Navya, and thank you all of you who have organized this talk. So let me get started. Thanks for that introduction as well. So let me share the screen. Let me know if you can see my screen.
Yes, sir, we can see.
Looking at the context and the audience, have tried to put this agenda for today's talk. I understand that most of the students here are studying in fifth semester, the third year, or some of them may be in MTech or in the final year. And so I have divided my presentation into first talking about the overall semiconductor or VLSI industry, and talking about an embedded product, and then further deep down into VLSI skills and how do we go about, what are the different career tracks available for you in VLSI, and specifically in ASIC or digital design and analog design. Of course, what is the challenge today the industry is facing as a whole? So, and what, how we can collaborate with academia, right? That's the last summary topic. As you all know, the semiconductor devices are used in many industries, many industry verticals. So I've tried to name few here, right? So automotive today, we are talking about driverless cars, right? So that's where a lot of semicon research is going on, and the chip development is happening to support automotive industry. Next is the consumer electronics. I need not have to name all the gadgets and the computing devices you are using. Those are consumer electronic products. All of them will be having VLSI devices. Medical electronics, right? So high precision diagnosing equipments and also the surgical, instruments would be having, right, the semicon devices. Avionics and the aerospace, right? That's the other important industry vertical where the VLSI devices are used. Industrial, the shop floor, industrial automation, and every day improving on the productivity in the in the manufacturing process, right? And if you look at maybe I know you would be having industrial visits. So if you look at maybe in Bangalore, we have a couple of them. Maybe it could be Toyota. What kind of the manufacturing process they have, starting from to manufacture a car, how the assembly happens, how the whole assembly line moves from one this thing to other. The process is also called lean process, right? So IoT, right? Internet of Things, and whether it could be smart lighting, smart homes, smart parking, smart cities, right? All about connectivity. Energy sector. So this is also, I think the future is going to be all our electric, the meter boards, what you have at home, right? Would be automatically recording these readings, and you will get the bill directly, right? Those one example could be smart meters we call. Communication, both wired and then wireless communication. Computing, right? The huge servers and the machines for computing. Storage, right? Storage is a way of life again. All the data. So now no more saving the data in the local storage, right? Is not the way going forward, or even already most of our data will be there in cloud. So that is also in the industry we call storage as a service, SaaS. Actually, Amazon and most of these big companies will provide storage as a service, right? And of course, all whether you name any biggies, like it could be Amazon, it could be Google, it could be Facebook, where all your data is stored. And of course we expect a reliability in terms of getting the data back actually. So now you don't bother to open a mail or open your Facebook account and assuming that no, today the access may not be there. So it is that reliable that all your data is stored somewhere, but you're guaranteed to retrieve it back, right? And of late, artificial intelligence, though it was there for years, today it is a reality. And many of your, these recent devices, what you are getting with the artificial intelligence and deep learning, machine learning, right? So it could be this, Alexa or this Apple's devices, right? All today we are moving towards artificial intelligence device usage at home. So pretty much I've tried to list few, and it may not be the whole. So, but every industry needs semiconductor devices. So overall, right, it's in order to relate to the financials, right, the market, right, it is close to 550 US billion US dollars industry. So for all these semicon devices, finally it's money, right? So it's business. So that is the volume of industry we are talking about. Overall, the spending and also the revenue. And the moment this is the volume of the revenue or the business or the market, a lot of spending happens. That is on the research and development of these semicon devices. So that's where you and all of us are involved as technical people to support this industry and in terms of contributing technically, right? So a couple of things to give. I've been there close to 2 decades. this industry has gone up and down. At least I myself have seen 2 recessions, and one in 2001 and 2 and 2008-9. So, but with all that, it has maintained a significant, the growth on an average, you can say 6.8%, right? And of course, so now with the advent of the artificial intelligence and artificial intelligence devices, so it has still continued to grow at 5.9%. So overall, right, there has to be ecosystem, there have to be partners, there have to be leaders in the industry to take this to the next level. So Semiconductor US Charter, most of these multinational companies in Americas, they have formed this group called Semiconductor Industry Association, SIA they call. Okay, so this is industry is providing or supplying overall 40% of the semicon products globally, and it employs nearly 250,000 people in US. Of course, the moment you have that many technical or the leaders involved, a lot of supporting jobs, close to 1 million, you can is created in US itself. So semiconductors are top 5 US export, along with aeroplanes, refined oil, that's in US. So US industry invests about 1/5 of the revenue in R&D, right? If we look at all, most of the MNCs, what we have, could it be Intel, AMD, IBM, or Cypress, all this, right? The work which is happening here is not manufacturing, it is the research, and it is the R&D, it is the development work, it's a cost, right? So that's where a lot of investment is going on, is even the people, right? So the salaries, all the things, right? The spending. So that is the funding which is happening to the research centers. Of course, we at India, right, we also have our own charter, that is, it is India Electronics and Semiconductor Association, we call ESA. And this is committed to development of both here, two things we see. It's brand India, and where it includes the manufacturing sector as well, not only the semiconductor, not only the semiconductor or the VLSI. So you have a lot of these companies coming together, a lot of startups, and also overall system integrators. If you take IoT kind of devices, it is not one company can do all. So it involves both the software and hardware, and till the cloud management and the data analytics. So end to end, right? A lot of companies have come together and then contributing for the India charter. Okay. So currently India exports, it amounts to 13% of domestic production, right? So, so whatever we make, right? This is, we are able to export 13%, and the volume is 45 billion. So of course, there is a genuine interest every day. Every year you see that ESA conducting and inviting all the industry leaders. Even this year also, it happened with all the world leaders coming and talking in the forum. Virtually it happened. In fact, it happened to be a very nice one because of this pandemic, and a lot of industry leaders, many of the MNC CEOs could able to join this event and then give their views about overall semicon growth. It was very interesting. It was 3-day event, and overall there is very good interest both from the government of India and also the industry leaders to take it to the next level. Of course, you all being in this vertical, that is electronics, you have a great future to pick up VLSI as a career. Of course, most of the time, though we I don't know, at this level, I generally say we shouldn't be talking about job, maybe, but it may not sound good for you. When I was also graduating, I was also looking for employment rather than doing anything else, right? But off late, I realized that we shouldn't be just looking at getting a job. We should at least, of course, we should look at learning when we are when we are studying, right? The holistic learning. It's not about just learning for the job or learning to get a job, or and also it is not about, okay, the moment you get a job it is done. No, it is just the one stage you have crossed, and in fact the challenges what you would face after getting a job is much more than what struggle you would have put just to get a job, right? So, but nevertheless, what is important for you all at this point in time? So where can I get in if I choose VLS as a career? Who are going to be hiring me, or where I can get seek employment at, right? So summarizing this, both India charter and the US charter. So we have one breed of companies which are product companies, which are, we call product companies which are fabless. Fabless means who doesn't have manufacturing units of their own. They are just design houses. So these are one set of companies, NVIDIA, Qualcomm, Broadcom. These don't have their own uh, foundries, okay? And there's one more set. So most of these, as you could see, the names are MNCs, multinational companies. So Intel, Samsung, TI, these are one breed of companies where they have their own foundry, their own manufacturing units to make chips, to make ASICs. And to develop an ASIC or an FPGA, right? So you need the tools, right, for designing, right? So that way, these three major multinational companies, Synopsys, Mentor Graphics, and Cadence, they make EDA tools, and then they support to all these companies who design chips. FPGA design. So this is one another set of companies, Xilinx, Aldec, Microsemi, and all. So of course, a lot of consolidation is happening. So this overall our industry, I would see a lot of consolidation. What I meant consolidation is, so one company getting acquired by the other. So recently, earlier we had an FPGA company. It was acquired by Intel, and Xilinx is pure FPGA company. So recently, that is getting acquired by AMD. So that way, a lot of this kind of consolidation you see, right? These are one set of companies which are FPGA design. So chip fabrication companies, see TSMC, Global Foundry, UMC, and a lot of Chinese companies, the Chinese and Taiwanese companies you see. So that is the other set. Only focusing on the foundry. So here, the fabless companies who designs, they will have to, depend on, they will design and then ship it to these people who will make chips, and then give it back to them for integrating hardware, software, and then checking and making the complete product, right? So, but some of these companies, they make the chips themselves, right? Of course, if you look at all these, like I said, most of them are MNCs, and then they have their India development centers, and that's what I think. Many yesterday I saw a news somewhere. 77% of our rank holders are working at this top 10 companies, right? That is the direction in which we are moving actually, right? And service companies, of course, in India. So we somehow identified ourselves in last 3 decades that we are good in providing services, design services, both in hardware and software, and even in VLSI. If you look at Wipro, HCL, and Altron, these are set of companies who are providing design services in VLSI area. What it means is, so they can design chips, and but they don't have their own um, products as such, but they support many of these companies. So if you look at these are customers to Indian services companies. So you could see in India itself, more than 100,000 engineers working in this sector. See, many of you, there is two school of thoughts here. One is, okay, VLSI is tough, and there is a huge entry barrier, is what I would say. If you get it on campus, definitely from with the core companies, that's one way to take entry to these companies. So other way, if you want to get into VLSI, but you come out of college and still you don't have a job, so you'll have to take up some trainings. Some of the training VLSI training institutes are set up. They will give 6 months training, and then further you can take an entry to this industry. But there is, like I said, entry barrier, and initially definitely 1 to 2 years it's a struggle. You will not earn much. So when you're looking at only the salary part of it, but definitely exponentially you will see a huge demand. Today I am also running design services. If I want to, in fact, 2 days back I interviewed one candidate with 3 years experience, and currently she is drawing 10 lakhs per annum, and then she wants some 12 plus. Otherwise, no, she's not interested. So after that you get into demanding mode, and then definitely companies are here to pay as far as the you're good technically, right? Of course, these are all indicative, not it varies from company to company, individual to individual. Okay, so just as an indicative, because in this context, I thought let me share this my view. Okay, so apart from this, you have broad opportunities as well. In fact, H1 and L1 visa companies process. They definitely expect minimum 3 years experience. After that, that could be one of your roadway, right? So of course, like me and many others, so you can also look at entrepreneurial journey after working in this industry for a couple of years. So I had about the industry overview. So what is VLSI, right? Okay, so it's basically a large integration, right? Very large integration, where we see millions and billions of transistors on one single die, one single DIE. It is one single chip or device. Know about the transistors, right? Transistors are fabricated on the silicon, right? And we represent a specific VLSI device with we attach to a technology node in what process it is manufactured, right? The latest technology nodes are 14 nanometer, 10 nanometer, 7 nanometer, 5 nanometer. So here the nanometer represents the gate length of the transistor or the FET. This represents the technology node in nanometer. So at times, people generally say, okay, it's the size of the transistor, right? At this level, you may know as such. So it's actually the gate length in the transistor or the FET. So basically, when you are designing, what matters importantly in VLSI? See, nowadays, I think, if you have gone to buy a laptop, you would have seen this particular thing where a lot of ads coming, where Intel 10th gen and Core i3, i5, i7, i9, right? So if you look at how you differentiate yourself, what is this? The of course, when you look at the bigger numbers are always efficient or good, but what is the generation? What is this? How I3 and I9 differ, right? So if you look at, it depends on, one is this, these are different uh, code names, or the core names what Intel brought in, I3, I5, I7, I9. It is about how many cores maximum it can have. This is 4 cores. You would have seen the dual core, quad core, octa core, right? So like this. So when the higher number, you get more cores, and also threads, the parallel processing, right? And with this you get the power. What here, there are two types of power. One is actual power consumed in the chip, and this power of computing, right? So the power of computing will be higher when you go for this latest generation of these latest cores, actually. So this is one set. I talk about generation, right? Intel also, see, you might have seen Core i5 fifth gen, fourth gen, right? Now the 10th gen. What this generation is about, just previous slide I talked about technology node. If you look at the same functionality, right? For example, i7, this 8 cores and the 16 thread, the same i7 chip, right, is made in different generations. Generation means here, these are all the code names what Intel gives, and these technology nodes are these. It is like faster processing, right? It is for faster processing, and these are the technology nodes over generation. The last today, if you look at this 10th gen, it is still 10 nanometer. Okay, and also and double data rate memory, what it supports from first generation to this latest, we are talking about DDR5. Again, this is also about performance and the throughput. Okay, and this could be Tiger Lake 11th generation, still not out. So they are talking, it could be refined version of 10 nanometer, or it could be 7 nanometer is the top. So it's all about power, performance, area. So area means how you can achieve more transistor, or fuse in more transistors within a small area is the challenge. And performance is how fast I can get, and the power, how I can make it is power efficient, means it should consume less power, right? So these are the 3 important targets what VLSI engineer will try to chase on. There are different technologies of this manufacturing, right? One is the CMOS, and this is a 2D planar implementation of MOSFET. So how each MOSFET is, or transistor is fabricated on the silicon is this technology, right? So this you study more if you are choosing the manufacturing process of it, right? And this is up to 28 nanometer technology. CMOS was followed. Next came FinFET, right? It is this source, gate, and this the drain. They arranged in this way, right? It's a FinFET technology. It's a 3-dimensional one, actually, right? This they in order to achieve high speed, higher switching speeds and lower power consumption, right? So with this kind of things, of course, you can get into the more of it, right? I'm just throwing you some words here, and then further you can study more. Okay, and so this is in fact followed after 28 nanometer. So this kind of FinFET transistor technology is used. So now off late, talking about and already doing research on C and FET, carbon nanotube FET, FET, right, where you have doped carbon nanotubes running on this dielectric, right, and this kind of arrangement. So they are planning to use in 7 nanometer technology, right? So if you look at overall last close to 5 decades since the Moore's law has been framed, right? This is the journey from 10 micrometer technology to 7 nanometer where we are today, and 5 nanometer, 3 nanometer, 2 nanometer. This could be the future, but of course, the Moore's law is coming to an end, right? How small you can go, right? There is limit, right? So of course, still industry has not given up, and it is continuing. So this is the how chips are made, right? From the silicon and then wafers and couple of processing steps. Then you you fabricate on each chip your circuit, and then this dies are, and then test them, package them, whatever not working, throw it off, right? And then tested package dies, and finally you make and then ship to the customers. This is the process at a very high level, the manufacturing process, wafer to chip. Okay. See, when you take a system, right? Yes, you have a silicon, right? So you have to finally build a product, right? A embedded product where you put software in it, and then you build a system, and finally, you ship it as a product, right? So this can be one form factor design, which may be within your gadget, right? In your mobile, right? So both hardware and software. So when you take one specific chip or ASIC or even FPGA, so you could have multiple blocks, right? The functional blocks, your application processor. And now depending on what application this is being used, you will have different interfaces, right? For example, right, if it is a mobile, it should have a Wi-Fi, wireless interface GPS, and the Bluetooth, right? And of course, the processing engine. So in earlier days, it was only computing, right? If you look at your early microprocessor 8085 or whatever 8086, it was just for computing. So later, audio video got added, right? Then DSP processor came. Now, of late, it is about gaming, right? Your graphics, your graphic effects. So then graphic processor, GPU. So if you look at today, we're talking about three type of things for computing. One is general processor, second is the DSP and DSP processing engine. The third is the graphics actually. So that way, the application processor would have all these three, or it could be separate, right? And which will interact with many of these peripheral blocks, depending on what, for example, it could be camera interface, it could be speaker, mics, and this USB, DDR, right, micro SD card. Like this, you will see in one specific device, all these interfaces, and you will have specific controllers, and finally you get the end, the interface level. Of course, the power at what voltage level it operates. So of course, this I just listed about what is the important with respect to the connectivity, what type of connectivity, what kind of the displays you would have, right, and the graphics and CPU when you're selecting, right, when you're buying a mobile, what you're looking at, whether it is it's a Snapdragon, right? And inside, what kind of processing it has, what frequency it operates, all this. Or even the connectivity, does it have NFC, right? Today, or any other interfaces. You look at, does it have accelerometer, magnetometer, right? Especially, can it count steps when you're running marathon, right? So, and audio, and of course, environmental conditions, where what region it has to operate. For example, very cold countries, right? So whether this device means you have to look at the temperature range, or automotive definitely needs high temperature, yeah, withstand extreme temperatures. Okay, just give me a moment. Okay, so that is about the system. So I'm just a little bit deep diving into what a VLSI device would have internally. Now, how do you go about designing a VLSI device, right? Typically, specification, right? First, you come up with the specification, what the end product is, and the block level, just like in the previous slide I showed, what are the blocks, right? And you come with the block diagram, and you implement, we call something RTL, register transfer logic, right? We use Verilog or VHDL to code RTL, and of course we verify. Gate level, we convert these Verilog or VHDL into gate level, and of course each of these gates would be having transistors, right? The transistor level, and fabricate these transistors on the silicon, right? And finally you will make a chip, right? And then you put the chip in a system, and put a software into it, and then that's how you make an embedded product. Okay, so these are very high level things involved in VLSI system. So that's where always, whenever any company who's doing VLSI, they will also have an embedded division, right? Because what is after this, it is about HDS, we call hardware dependent software, right? So we need to make embedded software and then port it into the chip, and then finally that has to work. Now, the VLSI device itself can be of FPGA type, semi-custom we call ASIC type, or full custom, which is having analog components as well. So full custom flow or analog flow. VLSI design would have these three, any of these three. So now a little bit I talk about each of these, right? What is FPGA and FPGA design? See, FPGA is a semicon device, right? And basically we use for building prototype. What is prototype? It is something what you make before you actually productize. So you want to make some test chip or kind of thing, or first you want to test it on an FPGA before you make an ASIC, right? So that's where we use FPGA. FPGAs are field programmable gate arrays. So the feature of FPGA is they are reprogrammable. They are reprogrammable, right? Once you make a chip, you can reprogram that. That's the advantage of FPGA. So because of this reprogrammability, so I said this prototype, I want to make ASIC, but I'm not sure, but once you make an ASIC, actually, if it doesn't work, right, you will have to throw it off, right? So, before that, you want to put the whole ASIC code here in FPGA, see that it is working, right? So that is what is ASIC prototype using FPGA. And you can even, one in FPGA, you can integrate like this, and then finally you can even test it functionally. And one more thing is you can even develop drivers for specific interfaces, right? So it is cost effective compared to ASIC. FPGAs are cost effective. So what are the limitations? They are somewhat slower compared to ASICs, right? We also call SoC, system on chip. These ASICs are called system on chip. At times, the placing the entire design, right? So any idea? This Intel Core i9, somewhere I read, it is having more than 10 billion transistors on the chip. 10 billion transistors. Now, when you want to put that complexity, that size of the logic inside an FPGA, right? It is difficult actually. So that's what he's talking about. The entire design is difficult. That's where industry has come up with emulators or emulation devices. It's a series of FPGAs, and you can put the complete ASIC code into number of FPGAs, and then as a whole you can test it actually. So there are emulation platforms like VLSI, Zebu from Synopsys, and one more Palladium from Cadence. So those emulation platforms are used. Okay, so some disadvantages of FPGAs are this. Of course, they provide capability, but not to the mark, right? So FPGA structure, if you look at, it will be having logic blocks, interconnection between the blocks, and IO cells. Okay, so I think you would be working with FPGAs, or you might have already been, right? So understand the structure. Basically, this each logic block is programmable, right? So basically, it contains logic blocks which can be reconfigured, and each logic block would have an LUT, right? Lookup table for making combinational logics. Here you can make whatever gate structure you want, AND or invert or some adders, right? Combinational circuits. MUX is used for selection logic, multiplexer. D flip-flops to store the output of the LUT. So this is typically, the structure of each CLB. Okay. So what is the flow we use for FPGA? So first is the design architecture, and we here also write RTL using Verilogger VHDL. We verify using test benches, and now we from this point onwards, we use FPGA softwares in order to convert these RTL into gates, that is synthesis process, and design implementation. It is about fitting whatever you have synthesized. You got the gates. Those gates structure, you are trying to put it in this FPGAs and route it, right? And that is this design implementation process, and do the timing analysis, right? That is the next step. And finally, you generate a bit file, and through your JTAG port, you program to this FPGA device, right? So that is the last part. So these first three steps are common for both ASIC and FPGA, and these are specific. For example, here in FPGA, you target a particular FPGA device, and then you do this. For example, each of these devices, they will specify how many IO cells, how many IOs, how many logic blocks, right? Depending on the logic blocks, number of logic blocks, and the size of your design can be fitted in, right? So that is the FPGA flow. Now, digital or ASIC design. So this is called application specific integrated circuit. So we make a customized design, right, for a specific application here, and they are very complex, and also more transistors can be fused in, right? And the technology, how we manufacture, I already showed you. Advantages: specific functionality, large production volumes, where NRE cost can be amortized across many devices. What is NRE? Non-recurring engineering cost. Basically, it is one-time cost. Okay, one time you are investing. So in order to bring out a chip, actually, so it might take minimum 1 year, right, from architecture till you get the chip, and then making it a product, another maybe 6 months, right? Overall, putting software and then testing it functionally, all that, right? So, but if that 1 year of manpower effort and the every money and everything, right? So will go waste if the chip doesn't work, right? Especially it's a celebration when the first time they call that as boot camp, right? Once the chip is fabricated, foundry sends back, and the design houses will put all the team together. Because I was involved in one of the boot camp where this automotive chip, the last project what I supported as a program manager, and there was a Intel team here, and I was at Aricent. So from Aricent, we were supporting the both design chip and also the software part of it. And the boot camp was at Germany, right? So Germany team was bringing in the board, this one, and there were some US folks coming in for the software. So it was all people coming together for 1 month and then bring up the chip, right? So very first time, if it gets booted, really it's a celebration. So day and night they were not losing time. So that way, but what if it fails, right? If it fails, really, it is very bad. Nowadays, I think with all these technologies evolving, our ASIC design and manufacturing process with the latest tools and technologies, so pretty much we are getting, more success in terms of this ASICs getting solved in the first go. Otherwise, you'll have to go for respin, right? Of course, that's the disadvantage, is only that in FPGA you have a choice to reprogram, but not not here. Right? Just like FPGA flow, we'll just briefly understand the ASIC flow. So here also we start with architecture, okay, and so at least you will know this is the device you are making. These are the blocks it should come. These are the frequencies it has to work. All these you will define. These are the voltages you are supplying. These are the inputs and outputs, right? Everything you will decide at the architecture stage. Next, each of these blocks, right, and also as a whole, right, you code and verify and then integrate, right? That is design and RTL coding. So you use very long, right? And further, you verify, that is functional verification. So you use simulators, and then most of you are aware of or already maybe using, right? These kind of waveforms you'll be looking at to debug what inputs you gave, what outputs you are getting, right? Is it all okay? Is the device working as per your expectation, right? That is functional verification. Formal verification, right? Nowadays, a lot of time is getting spent in the simulation. So many checks, the negative verification is done using formal verification. So this whole thing we call this front-end activities, okay? So architecture, design, RTL coding, and functional verification, all this, we wrap it up saying it's front-end, ASIC front-end activities. So next process is synthesis and STA. Synthesis and static timing analysis. So using synthesis tools, at every stage, we make use of EDA tools, electronic design automation tools, and from Synopsys, Mental Graphics, or Cadence. And so here, synthesis tool converts or translates this RTL to gates. If you look at, so there's a D flip-flop, if you could see this, right, or some inverter, right? So just it's a gate equivalent of RTL here. RTL means the register transfer logic. So what is RTL? You're describing these blocks, how it has to work, right? So that in the design, okay. And so if we are representing in the circuit form, right? That's the gate structure. Now you do gate level simulation. So you have verified RTL at this level. You translated this, and then with this gate, you just do the gate level simulation verification whether things are still working as per this, right? So still you should see in the waveform with the gate level simulation things working. Only thing is you may not see these code. You will see the gate structure. Next is DFT. Okay, what is STA? Static timing analysis is you will have for everything timing budget. Okay, whether within that budget the data is getting transferred from input to the output, right? So within the circuit, for example, so this is, this XOR gate will be having some delay, NOT gate having delay, these flip-flops will be having delays, clock to Q delay. With respect to this, right, all these delays we will consider, and in the sequential circuits, the setup time, hold time, and how do you determine the maximum frequency of the clock, right? So those clocking budgets, right? Let us say to move from here to here, there is a budget of 10 nanosecond. Within 10 nanosecond, whether the signal goes from here to here is what will be checked in STA, but not by simulation. It is static check. This static check. It is like budgeting from one place to the other, but you're not traveling. You're saying that okay, from Bangalore to Mysore, I want to travel. You're budgeting 3 hours, okay, but you're checking, the budget whether 3 hours is okay, right? You're comfortable there, but actually when you travel, right, that actual traveling you will check by simulation here, gate level simulation, right? So pretty much we'll also keep some buffer so that when STA is done, pretty much you are good. You are good. You are keeping buffer, enough buffer so that definitely you will reach within that time. So like that. So that's the code of STA. Next is DFT, design for testability. So for you, when I'm talking about all this, it looks to visualize, okay, the silicon and this nanometer, how the whole thing works and how whole thing, right, even when the chip comes back, how to test, right? Those kind of questions may be coming to your mind, right? So DFT is designed for testability. So when the chip comes back, so how do you go about testing whether the things are manufactured properly within the chip? For example, now you have a silicon, the foundry has manufactured and given it back to the design house. How do you know whether all the transistors, the gate structures internally fabricated, they are good? So for that, we will give some, when during the design itself, we will make a provision to test it, right? So just a typical example I can give is earlier houses, they were concealing all this um, plumbing, this thing, right? All the pipes they used to conceal in the wall. So nowadays they will have a conduit where all the pipes can go in, so that if there is any leakage, you can go and repair. So earlier once the pipe goes bad, even your building is leaking, right? So here, what does this mean is, so you have this kind of circuitry, and within the chip with this is embedded, right? This is manufactured. Now, if this flip-flop is not working properly, how do you know? So for that, right, I will introduce some scan structures where in front of all these flip-flops, I will add a mux, and then from here, there is a JTAG port, I will provide at the chip boundary. Through JTAG, I should be able to drive into these individual flip-flops and then make sure that, okay, whatever I drive, I get it at the output. Test mode, right? So that is designed for testability. So that I am making when I am designing itself. So that's where after synthesis, you make every flip-flop scannable, right? That means I can control from the input pin of the chip. Observability and controllability is provided using DFT techniques. Okay. So and I make all these flip-flops, different scan chains here. And once the chip is out, I will use a tester, and from the tester, I send the stimulus here to the chip, and then I will select specific scan chain, and each scan chain would be having number of flip-flops. It could be some 200, 300 flip-flops. Like this, in the whole chip, you will see many scan chains, okay? Many scan chains. And the advantage or the target of the DFT engineer is to bring more than 95% of these flip-flops, making them scannable. Right? The flip-flops, of course, for the combinatorial logic testing also, there is something called ATPG, okay, automatic test pattern generator, and then we apply the patterns and then we check, okay, when I give this XOR gate, this 1, 1, what is the output, inverter output, right? All this we will check. So we are checking basically, we are making provision during design, but actually we are using them for testing once chip is out. Okay. So in order to see any manufacturing defects within the chip. So this process is called automatic test equipment test. Okay. So of course, after the scan structures, ATPG are added to the design, we take it to the physical design. So physical design is about you are seeing these gate forms, and all these, we also call this as gates or standard cells. Place all these standard, and like this, many blocks would be there like this. Now these blocks you place here, and then route them, and supply clocks, supply voltage, right? All this is done in physical design process. So after this, also you dump out the net list and also the delays, wire delays, gate level simulation with timing delays you can do even next level after this physical design process. And you do the physical verification. So this verification, these verifications, how they differ is, this physical verification is about checking the foundry rules. What it means is, now I am sending this Gerber or this design database to a foundry, that is a TSMC. TSMC, Taiwan Semiconductor Manufacturing Company, gives set of rules to the design house that these are the rules you should have followed for me to transfer this graphics to my chip, my silicon, right? So those rules are checked with the physical verification. So it could be antenna rules, it could be routing rules, right? A lot of other things, right? So will be shared by the foundry. And finally, this Gerber, what we release to the, is not readable, not human readable format. Of course, it can be imported with the foundry with the tools is GDS, graphic design stream 2 format, and that's the one which goes to the foundry. And the whole process we call this as backend process. And finally, this what they make on the way for the fabricate, and then finally you get the chip package out. So overall, in this whole ASIC design flow, you see these couple of things. So what is in it for you? It is not one team or one person can be expert at all these different streams here. Okay, so our industry looks at this design engineer, verification engineer, synth STA is also separate. Actually, I need STA engineers, right, and TFT engineers, physical design and physical verification. So this is how the skill sets are today split. Okay, so in fact, if you go back to 80s and 90s, one person was doing everything, including the board design, including writing software, right, driver and everything. Say today, so forget about software, hardware, their embedded software and the boot, and if you look at the ASIC design itself, analog digital is one set of category, analog design FPGA, but within the ASIC design itself, these are the different streams what we have, and the split. So this, you are all familiar with this. We call these as standard cells. Okay, the basic gates, the universal gates. NAND and NOR are called universal gates, where you can represent all the gates using these two. Okay, so these are standard sets. So now the design activities, like I said, the different career paths in ASIC design, the stream, front-end design, architecture design, and RTL coding is one. You should be skilled at, see, for all these, Verilog is common. You should know Verilog. Okay, so the basic part which is required. Verification, in addition to what you do is functional verification, gate level, coverage analysis, all this. In addition to Verilog, today's system Verilog, UVM, right, and different methodologies, right, and the scripting, automation is the way. So whatever skill you do, automation using nowadays, Python, you use Python for automation, right? FPGA design you can choose, where you need to be good at, again, Verilog here, and verification knowledge, if you have, definitely will be very helpful. See, today, we get requirement like, do you have FPGA engineers who know system Verilog and UVM, right? DFT, like I said, one should be good in JTAG, understanding of the tap controller, scan insertion, ATPG, MBIS, TELBIS. These are all different things to check the memory built-in self-test, logic built-in self-test. These are testing the logic and the memories. Okay, and synthesis and STA, like I said, this is one. And the back-end structural design or physical design. So floor plan, place and route, CTS, and power plan. So these are all the things, and the skills required are these. So of course, after this, it's a post-silicon validation activities once the chip is back. Okay. So if you have time, I can walk through one of the design. Basically, how you go about, because why I put this is looking at what is the takeaway. Yes, I'll talk about this industry and the high level, but now to start with, what you can do, right? Especially, can you take up some projects in VLSI and then do what could form a project for you? Of course, subjected to your professor's, approvals. But what I suggest from industry side is, if you do this, it's a very good candidate, what industry can appreciate as a project, right? I've taken here on simple protocol based memory design. Okay. So now when you subdividing the whole system, now you are getting into the specific interfaces and the blocks. So ARM is a company, advanced risk machine. So they came up with embedded processor architecture called AMBA. Okay, so AMBA, they introduced APB, advanced peripheral bus, for the slow interfaces, and AHB for high performance, and AXI interface for, that's a third generation for a higher performance, right? So now these are all the different bus protocols. Okay, so for example, what is a protocol? Set of guidelines. For example, now when you are when you want to transfer the data from one device to the other, you have to follow certain rules. What those rules are defined with respect to first clock, second clock, third clock, right? So how you need to drive the data, and the other device how it can sample the data, right? Those are the rules defined in the bus protocols here, right? Or in other ways, there is a packet-based data transfer which happens in Ethernet, USB, and PCI Express. These kind of protocols. What happens there? There you have learned about OSI layer, OSI model. Sorry, OSI model. So you have different layers, where transport layer, data link layer, physical layer. The data transfer happens through layers. Okay, from application layer it goes to transaction layer, then data link, then it goes to physical layer. That's where media attachment is there. It could be, right, a high-speed fiber connection, and the receiver will receive from the cable, and further in the physical layer it moves to data link and to the application layer. So that is the other set. So there again, Ethernet protocol, how the packet format should be and how the data transfer should happen. So that's the protocol. So now here, when you look at any system with embedded system, there will be embedded processor, and you will have bus interconnect internally, and this bus is attached with memories or the IO devices. And one such this thing here, this is a HB interface here, high speed interface, and this is a APB interface. So you can select, you can have up to 16 peripherals here, and I have seen shown some of these, UART and timer and all these low peripherals. Now let us say I want to design on memory block 1K into 32 and then attach to this APB interface, right? So now this block I have just blown it up here. So this is APB interface, the signals, inputs and outputs I have shown, and here the memory, right? So now all that you can design this block and you can verify, and for all the cases, right, as per this protocol, right? So that way you can try it out. Okay, so now here, when you go about designing, you will have to see these are the signals, and then here APB slave state machine, right? So now before you go and then doing this, you should know how to design, how to write Verilog code. What are the prerequisites? Prerequisites for this is you should know Verilog. You should know how to design using Verilog, how to verify using Verilog. That is a prerequisite. And of course, the usage of tools, how you can do that using the tools, right? So it could be, even for you, of course, you may be having Cadence toolset from Entupal at your college, but even otherwise, Model Sim student version is good enough for simulating these kind of examples. Or Xilinx Vivado, which is available freely, is also good, good enough, right? So it's all you can, out of your interest, you can go and then choose to do VLSI projects, and very interesting, right? Okay. So these are all the signals. Let us say this, just like your microprocessor, microcontroller, what you have studied, where it has chip select, it has clock, it has some, write data, read data, and the control signals, read or write. So this specific protocol has similar signals where the chip select and then address, right, enable, P write, this 1 means write, 0 means read, P ready, this in the protocol, the device can say I'm ready or not. Whenever a transaction comes from the processor, you're mimicking processor here using test bench. And when you write, and then whether it can acknowledge the data or not can be indicated by P-ready. Otherwise, right, it can make processor to wait. And similarly, read data. So it can give the data, whatever processor is asked. So it is asking through this address. So of course, this memory. So you can design this. So these signals, like I said, these are all the signals. And so just the timing waveform, I want to give little time here to explain a protocol. So P clock, this is a synchronous system we are talking about with respect to the clock. The data is driven and sampled. So P address, right? So if you look at P write, P address comes from the processor. P write, processor says write or read. 1 means write, 0 means read. P select, you saw some 16 peripherals there. You can select any one of them at any point in time. And P enable, as per the protocol, first clock cycle is 0, second clock cycle it is 1. PW data is putting for this address, this is the data. And P ready, this is coming from slave, means your design. It can say whenever it is 1, I am ready. When it is 0, not ready, right? So that this is APB write access. So if you look at very first clock cycle, that is idle cycle, where all these signal status is 0. So next is setup cycle, where you say select is 1, P enable is 0, and you're putting address and data. Now the next is access cycle, where you're enabling the transaction, and as long as this ready is 1, it will sample. If ready is not 1, if it is 0, see this is 0, the whole transaction got delayed till ready is 1 here. Ready is 1 here. So this is when the transaction is acknowledged by the slave, and actually this will be sampled by the device here, and then finally you processor is ending the transaction here, if you look at. Okay, so this is how one write access works. If ready is until ready is 1, it waits here. That's what shown here. If ready is 1, again keep transferring. If ready is 0, go back to reset. Similarly, read access, you can imagine the same way, except that this PR data comes on PR data from the device, right? And P write is 0 here for read, and of course ready has to be 1. Okay, so here you see this with respect to this clock, assertion happens. With respect to this clock, sampling happens actually. So that little bit more technical, you can study further and then see the driver and the receiver samples, driver drives the signals. So this is about simple APB protocol. Of course, I have written RTL, and okay, this is too much for you at this stage. So you can write, and you can write the test bench. Normally, I have seen people directly use this input to the waveform. In the waveform you are okay injecting inputs. No, don't do that. Write a test bench, right, where you can write the test bench and then instantiate this design, and then write tasks based test bench where you are writing the data, right? You're driving the data as per the protocol and also receiving the data as per the protocol, right? And you can also write some task to check the data. For this address, PW data you pass, PR data you pass, it will check and then tell you whether the data is matched or not. So like this, you go for full-fledged test bench writing, right? Of course, your professors can guide you further. The basics of Verilog, if you know Verilog, the design and verification concepts, you'll be able to come up with the design of the test bench. So these are all the tasks. So finally, you are simulating this, for example, P address and P enable, whatever waveforms I explained, you are getting it in the simulated form in your. So this could be a good example for you to. This could be the output what you can show as a project output, right? How it is behaving. A lot of variants you can do. For example, ready, you can delay ready for long and then see whether design works, and give ready all the time whether it works, and here all the transactions for all the addresses working. Many things you can try. It may be looking simple for you, but you can complicate to the maximum actually here. So as you could see this PR data, what I have done is one address A, I have written this data, right? The writing happens when P enable is 1, P write is 1, and chip select is 1. Here the write closes, and for the same address, read is initiated because chip select is high here. Back to back I have triggered, and here you see first clock P enable is 0, second clock this data, if you look at the same data, you are getting it here. So this way you can go and do this project. So now that is about digital. So far I have covered, apart from this industry overview, FPGA design and ASIC design, or the digital design. So whatever project I showed, the same code after simulation, you can either take it to FPGA or take it to ASIC. In both the ways actually. So in FPGA, you target a particular device, you fit the whole code into the FPGA. In ASIC, you go through the physical design process, implementation process, all that, take it forward. Now I come to this full custom or the analog flow. Okay, that's about digital flow. Analog flow, it's more about the transistor characteristics, and you're getting deep into how you can make transistor efficient in terms of, again, power, performance, area. So because transistor, how fast it can switch, right? And how much power it consumes, and how far, one is the speed, other is the area, and power, how much power it consumes. So those are the things which will be, but in the analog, you are looking at optimizing all the three parameters here in the full custom. That's why it's called analog flow. So what happens in digital flow? One thing I forgot to tell is, now I don't get into this level for digital flow. I use the ready AND gate, OR gate available, right? Those are called standard cells, and then I take it forward. That's why I call semi-custom. It is not full custom. You're not customizing till the end, right? So in ASIC, what semi-custom, what I do, I will use ready-made components. For example, now already components are there, I am assembling, like that you can imagine, right? But in full custom, you're making those motor parts also. Okay, means what? The basic raw materials, right? Here the basic thing is transistor. You get into the transistor level, and then you characterize, right? Transistor, you study more of it actually, that and performance improvements you do at the transistor level. Look at now, so you are making it a brick level, and then and finally you are assembling and building a big house, right? So, and in ASIC, I don't worry about, I get the ready blocks, I just assemble, right? So that's where full custom takes more time, right? And it is not only the design time, it also involves the modeling of these transistors. That's the analog flow. So your specification, architecture, circuit level description I get into. Okay, circuit level description and layout, and the fabrication. So more about, so these are all the analog components you can look at in any chip. IO ports interacting with the external environment, they'll be analog, right? Phase lock loops, there'll be analog PLLs, right? They use it for locking to a particular frequency. Regulators, right? Voltage regulators, ADCs and DACs, audio and power amplifiers, converters, right? And this voltage converters, right? So there'll be one, this is operating at 5 volt and this is operating at 3.3 volt, so this has to be stepped down, those kind of converters. So all standard cells you have to optimize, and RF communication blocks, sensors, media interface, many more. You can imagine what analog components you look at, right? So analog circuit design is one of the career path for you, right? And analog layout. This industry wants nowadays there is a memory layout. Yesterday I received a query that, do you have memory layout resources? So memory layout engineers. So everything is becoming specialized nowadays. Actually, it is not one. You cannot find in one specific resource all the skills. So this, it's becoming narrow in terms of the skills. So overall, with this, FPGAs, semi-custom ASICs, full custom analog flow. So FPGAs are field programmable, semi-custom you use the ready standard cells, and full custom, even at the mask layer level, you're involved, and then you characterize. All right. So rest all depending on your this thing application. For example, specialized general digital logics, you go for ASICs, and then specific microprocessors, very optimized For example, one project I was working on in somewhere in Wipro in 2006-7. So there was one company called Ajia. They were making a gaming engine, and they were using embedded processor, that is MIPS actually. And in addition to that, they were designing a vector processing unit or vector processing engine, VPE, and they were having their own. They were coming up with the same their own instruction set, which for gaming processing. Actually, they wanted to give a. They were implementing physics algorithm. It was for a gaming chip, and to give the real effects of the on the screen when you are playing the game. For example, with a particular force, a person goes and hits a tree, right? And in reality, what could happen? They are emulating, right? So to that precision, that okay, whether how the what is the consequence, right? So that way, specific specialized things when they're going for, they'll go for this full customer analog example. Okay. So when you are looking at your career now, keeping yourself open for all the interested areas, right? I am not trying to confine to only one digital design or analog. So I'm telling what are the different things you can get into as an electronic engineer. Other is high-speed board design or the system design, right? So for example, you want to make this board, this ASICs or FPGAs you are getting, but what are the considerations you want to build or design this board, right? You do a lot of considerations where AC analysis, right? Electrical analysis and DC analysis, voltage related, right? And both timing and also the voltage level, and also, you create schematic for the board, and then you make the PCB, assemble these, and test it, right? After that, this functionality will be tested by the software. So that is what is involved in the case of system design of the board. This is also one of the skill set, right? Industry wants actually, right? So for this also there are tools. You what board you want to make, you design entry, you make all these parts with inputs, outputs, and then here in the schematic you connect one to the other based on what connections you need to do. And this floor plan PCB layout is this layout complete. Earlier, I talked about within this physical design, physical layout is this, right? That is ASIC or FPGA, but this part is board level. Yeah. And packaging, right? Here also system design. So definitely you need to be good in all these electrical characteristics and analysis. This is one of the thing. It's interesting actually. So even this also you can take up. Okay. So of course, embedded software, all right? So microprocessors, RISC and CISC, two types. So complex instruction set and also reduced instruction set. What we deal with in the embedded applications, it's all about RISC processor, okay? And the CISC processor, where it will have minimal number of powerful instructions which can do many things on the chip. Here, that is not a criteria for you. You go about, you don't know how the instruction set is for your Intel chip, right? And accept the boot code what they write and then put it to the chip. Otherwise, rest all, you don't worry. You write some program and then you execute, right? That's where this complex instruction set computer is large number of instructions of variable length and more cycles to execute. Here it is restricted. When you talk about RISC processor, you talk about pipeline structure. How many stage pipeline a RISC processor has, whether it is 8 stage or 4 stage, 12 stage, like that. So all are interesting things, what happens in each stage and why pipelining, right? All this in order to get the speed and performance, right? So embedded software, basically, when you talk about embedded software, you should be able to write a very efficient CR assembly code because you are putting inside a chip. Why it has to be efficient or small? because you have a memory restriction to put your software into the chip, right? And so that is embedded software. Of course, there are Autos, right? And VxWorks, embedded Linux, and all this, even Android for that matter, right? And so each of these, they have their own platforms and the services. If you look at bootloaders, BIOS, basic input output system, firmware development, so kernel, so the device drivers. So these are the skills what one should possess to take embedded software, embedded system software career actually. So what you should be good as, you should be good in programming and logic and embedded C, writing efficient C or assembly, and also processor architecture, right? How things works, and later, okay, how the kernel and other things will come in. But what is basis for it is how the whole embedded system works and the processor works, right? Because you are writing software for the hardware, right? And at the very core level, you will be studying how many registers this particular chip has, how to configure them, right? And what configuration, your settings. Configuration means what setting. Your software comes and sets this chip to operate in certain way. For example, now when you power on your mobile, the very first message what you will get, where it's coming from, that is coming from the boot ROM. Boot ROM, that's permanent memory. That either, if you have Samsung phone, whatever you get Samsung, the character by character that is stored in the memory ROM, and after power on, processor goes to the comes out of the reset. Very first instruction what it gets is that character reading and displaying out to your display screen, right? So that basically is a boot ROM, right? So you are getting into the that level of software development if you're choosing. Of course, then higher level USB driver or Ethernet driver, you're making a driver development, all right? So those are the things, right? In embedded software, what will be involved. Okay. So these are the topics I had, and of course I'll summarize. So of course, this some data I took actually, right? So more than 16 lakh engineering graduates comes out, in India every year, but about 64% of them are doing non-engineering jobs. Not a very encouraging statistics here, but that's a reality actually. So the employment skill index of Germany and other developed countries is more than 90%. So what it means is the academia is producing engineers with skilled engineers who can take up the jobs and do or perform jobs once they are out of the academia. Okay. So India's skill index is still less than 10%. Okay. And it's not why these are all coming from. See, even though companies give offers, and right from day one, not all of them are engineers, are not productive. They have to take them through one more set of trainings, right? So for 3 months, 6 months, and all that. So that's what is happening in the industry. Okay. Okay, so today, one thing what is happening in VLSI, like I said, so 90% are fulfilled through VLSI training institutes. So because that's where, even though electronic engineers comes out as freshers, so they will not be familiar with all the things involved. That's where they will have to get into training institutes and then equip themselves and learn. And then, so industry challenges for that is, these are the challenges, right? Power, performance area, and time to market. Now, all this, right? Definitely, freshers would not be knowing. They will have to walk them through and then make them learn, right? And engineering resources, they expect one is hands-on skills, right? And they should be aware of latest tools and technologies, and little and grooming this VLSI VLSI skill is hard. I admit openly, because finally when engineers do only, they learn and they can demonstrate. They have to demonstrate. Actually, it's how about, now it looks all rosy when I talk about all these things, but definitely when you get in and then start doing the simulations and further, you will really see the challenge. So that way it takes time for to learn. Okay. Because companies don't have much time to train, so that's where these training institutes are, helping there. Of course, academic challenges, you all know, I don't want to tell, right? So there are some gaps there in terms of no one to be blamed. Of course, in one of the forum I was suggesting how many of industry people we are ready to go back to the academia and then teach. Really, we are complaining that academias are not producing engineers of what we want. Then who's contributing, right? So if we also need to go back and then support them, actually, right? They come up with one strength and then we need to complement in order to, because why I say this is, this challenge is not there in developed countries like I mentioned, Germany or in US, because there is a lot of collaboration happens between the industry and the colleges, right? So in fact, when I was in US in 2000, so along with me, there were interns coming from colleges also were part of the project we were working with, and they were also given one module, and equally he was also doing the same work what I was doing, though I'm experienced, and then as a fresher he was able to do it, right? So those platforms were given by the companies, and also the engineers were also equipped to do it, actually. So both the ways. So that one, it's happening in many ways. That's how I think these kind of things were not there earlier. Colleges inviting industry people and addressing, and only management talks were happening earlier. Now technical talks are happening, and the tools and other things are provided, and a lot of internship programs are being conducted. And of course, I think Damodar, if he has joined, he will address about what kind of internship programs NTPL has for you, and also what kind of career builder programs we have for you. So that is this thing as a, we as a team, right, collaborate and then build this ecosystem, um, and supporting each other. Okay, so of course what industry expects is you should be good in concepts. Good in concepts means, right, it is really, you should I mean it, until that concept is clear, no, we should not sleep, actually. To that extent you should be very clear. Otherwise, no, is pass it on, pass it on. How many things we have passed on in life, right? Whatever it is, right? And they will come back to you someday, right? And there is no escape for many things, actually, right? If not today, tomorrow I have to do, right? So that's what there is a, not a very good word, better be a fool today because you expose
ನೀನೇ ಹೇಳುಮ್ಮ.
other extreme which we are facing. To recent example, what I wanted to, I can give one is, I have hired an engineer and I have sent to the customer within 2 weeks, and the customer has sent laptop to his home, and he has got it, and then he has started working. Within a week you don't want to work, you want to resign. One case. Second case, he joined. After 1 month I got a better offer, I am resigning after 1 month, right? So these are also killing the whole ecosystem, and that's where what's happening. Industry has to protect their own investment and what they are putting on training, and their other costs. They are coming back with the employment agreements, points, right? And yesterday, someone was saying there is one company who has come up with a bond, 3 years, 10 lakhs. Within 3 years, if you leave, it is 10 lakhs. You have to pay and then go. So people are very, and that is also maybe younger generation. Okay, they are very anxious. How can I get 10 lakhs today, right? So for this thing, what I say is you will get it, but you have to make your foundation strong. You work for 2 lakhs today, make your basic strong. Anyway, that is going to come, right? So with all these things, right? So there's a on the other side what industry is facing, and the same set of people will come, sir, I need a job. The sir has given job. After that, you show this attitude after 1 month, 2 months. Suddenly you say, my family has big financial problem, right? So it was there, you were okay. That to this person who has resigned was without job since last 6 months. We as sitting on the other side, we face these kind of challenges, right? We need committed, loyal people, and definitely they will be rewarded. They will be rewarded. It is not that industry exploits that way, right? So anyway, so that is the other challenge. So take care of all these things. Everything is important. So way, right? So that's all I had. So quickly. Not sure the forum I can have this. Okay. I will hand over to Damodar from Entipal Technologies. In fact, Entipal is our partner, or we are their partner in terms of bringing a lot of programs in VLSI to the academia. And I would request Damodar to address maybe some 5-10 minutes. Damodar, you are muted. Unmute yourself. Damodar, can you unmute yourself?
No, excuse me. He will be made as a co-host and then he can speak.
Oh, okay. Okay, no problem. Please take care of it.
Yeah. Hello, Shiv. Am I audible?
Yes, yes, go ahead.
Yeah. Thanks. Thanks, Shiv. Okay. So, as Shiv has given information, okay, right, regarding the overall industry scenario, okay, right. Let me share the final glimpses of, okay, right, what is the typical scenario which many engineering graduates are going through today. In fact, as Shiv rightly pointed out, it is not the opportunities which are really hurting us, okay, right? Because according to one of the survey, okay, from Government of India, Ministry of Skill Development and Entrepreneurship, and as well as MIT, Ministry of Electronics and Information Technology, uh, the ESDM, Electronic System Design and Manufacturing Industry, by 2025, this is the forecast given by the Government of India in the year 2015 and 16. By 2025, India would be in need of, okay, right, uh, 2.78 million, okay, manpower, okay, right, for the industry. What is this means? We are really looking at, okay, right, a 2 crore 80 lakh working population only for the electronic system design and manufacturing. So ESDM includes chip design, right, both hardware and the software, and also electronic system design, which board design, which Shiv pointed about, then service, repair, maintenance, and everything, okay, manufacturing. So all these things. So if you look at the statistics, interestingly, what Shiv has shared, right, Indian ecosystem is producing 16 lakh engineers, and for your information, circuit engineering branches are hardly producing 3.5 lakh to 4 lakh engineers only. Whereas ITIs, industrial training institutes, polytechnics, and JOCs, job oriented courses, institutions, all of that put together are only producing 15 lakh circuit engineering branch engineers and technicians. So if you look at it, the historical background of last 5 years, where we are in the midway through for 2025, in the year 2020, still we are falling short of nearly more than 2 crore working population for this industry. And you might have seen the announcement from government of India where they are planning to deploy the Vani, okay, that is internet access at the grassroots level, which already, by the way, they have done it, okay, right? Today you have the free internet access up to the district headquarters level. Now the government of India wants to take it into the gram panchayat level also, where each and every small shop outlet, even a rural house, a rural place, can have the free internet access. Now what is this internet access means for all of you? It means lot of electronics, lot of hardware, lot of software, which will be going into the lives of people day to day. Now, in spite of all these things, another interesting statistics which the government of India has projected, and even Indian Electronics and Semiconductor Association, is that in IT industry, the employment conversion ratio, that means out of 5 engineers, right, if they attend the interview, they will get uh, they will uh, get a job. Okay, 5 engineers, okay, 5 is to 1. Whereas in case of semiconductor industry, the ratio is staggeringly in the range of, right, 50 is to 1. So now you can imagine, in order to fulfill the requirements of, okay, right, in order to fulfill the requirements of 2 crore working population for this industry, how Herculean task this industry is doing. And that is why the engineers are also hopping the companies, okay, from one company to another company, because taking an engineer into the threshold of delivery is a big challenge for the industry. But after that, the challenge is of retaining them. So as a result, the industry has their own, right, pain points. And at the same time, the young engineer who is aspiring for a career, okay, in the core engineering sector such as VLSI and electronic system design, they also have a challenges, because they don't know what are the skills which can make them employable. So at Entupal, okay, right, being a 10-year young startup organization, our learning is that these are the typical issues what we have seen with even our own hiring manpower, okay, right, from the ecosystem. So typically the students have issues like whether they have to focus on the exam marks or hands-on experience, and if they have to choose the technology, what kind of a technology they should be choosing, whether they have to choose VLSI, embedded, or communications, or IT sector, or within IT sector, what they need to choose. So those are the typical questions what they'll be lingering around. And plus, what type of a projects to choose, whether we have to choose projects on the simulation, we have to choose the projects on the hardware, right, we have to choose the projects on specific aspects. So those are the typical questions, and what kind of a preparation which is required for the career. So these are the typical questions what many of you here with us, you also may be, right, going through. So in order to address these things and fulfill our own manpower requirement at Entupal and as well as in our ecosystem, in fact, we are working with our partners like Excel VLSI also, right, through different types of initiatives and the programs. So in order to address these requirements, we are offering short-term programs and industrial training and internship programs, which basically brings in insight on the technology and the industry orientation. Then career builder programs. So our short-term programs will be of a duration of up to 5 days, whereas industrial training come internship programs will be of the duration of 4 to 6 weeks, and career builder programs will be of 4 months duration. Now, what is the uniqueness of our programs, right? So our programs are both classroom based and as well as online mode. So depending upon your, right, interest, right, you can choose the classroom and the online mode. And in both the modes, the programs are strongly supported with the mentorship and technical support from our end. If you choose even the online mode, okay, right, you will go through the live sessions, and you will also have the assignments and the projects with the tool access, right, which are basically being, okay, right, supported by us. So once if you work on those things with the help of the live sessions and as well as assignments and the projects, then it takes you to a certificate of completion. And not only that, if you want to, right, pursue your interest in a specific job domain or specific interest, for example, Shiv talked about, right, design verification, right, and physical design, analog circuit and layout, FPGA design, so many other things. So each one of this job role includes multiple steps of growth plan. So you can start with any particular plan of your choice, and you can take up the online training or classroom based learning and work on those individual modules as a part of your learning plan one by one. And that each one level one, when you complete, you get a certificate of completion. And once if you complete all the 4 levels or 3 levels in the learning plan, you will be eligible for a certification. And that certification helps you to, right, attain a career, okay, in the industry. And at the same time, it also helps you in your higher studies and the specialization what you may be looking at. Then how it is really possible? Because the certificate of participation and as well as the certification process what we have enabled, it is being recognized by National Skill Development Corporation of India under Skill India initiative. And this certification is recognized by all the industry ecosystem in India under Indian Electronics and Semiconductor Association, which has more than 500 plus registered companies under them. And plus, this certification is also recognized by the PSU's public sector units like BEL, ISRO, right, BHEL, and various other companies, and even a lot of research labs under DRDO. And further, the government of India has joined hands with right Western counterparts like Germany, US, and various other countries. And this skill certification, what you earn, it is recognized even in the Western universities and as well as even in, right, Western hiring companies also, or industries in those countries also. So as a result, the learning progression what we are facilitating for the academia network, okay, right, as a multi-physics engineering organization, right, is going to help you, right, to get the recognition. And remember, we are offering these things not only in VLSI, we are offering it in multiple engineering verticals like IoT, data sciences, machine learning, and AI, where the programs are recognized by NASCOM, okay, which is the software, okay, governing council equivalent to Electronic Sector Skill Council of India in electronics industry. And similarly, we are offering a program on RF and antenna design, which is recognized by Telecom Sector Skill Council of India. So these are the value propositions what Entuple is bringing along with its our partners like Excel VLSI and as well as other partners. So if you need any information or any clarification, in fact, various academic institutions across India, they have already adopted this learning framework into their curriculum from the second year of engineering at Dayanand Sagar College of Engineering, right? If your team is interested here, this message specifically I'm sharing with the faculties. If you are looking at adopting this framework, right, so that you can complement to the curriculum of yours, okay, so that your students can get a opportunity to own the industry desired skills in the campus, you can also assist them, and we are happy to assist you in that direction, where the learning plan can go from the second year of engineering, so that by the time the students they complete their final year of engineering, right, they might have completed the entire learning plan, and along with that they might have done module level projects and final project, which basically entitles them for the industrial internship training as per the guidelines of AICTE. And further, students can also take up the certification, and your training and placement cell can share that information to the hiring companies which are visiting your campus recruitment also, because the Cognizant or even Wipro and Infosys And lot of design services companies also, they basically look at this certification, and if a engineer confidently floats that competency, okay, right, in the evaluation process, the hiring companies, even services companies of our country, they would definitely prefer the engineering graduates to, right, put those trained and as well as competent resources into the core engineering vertical. So being in the helm of affairs, okay, right, in few of my earlier employers, okay, like Lucent and as well as even Xilinx Mentor and as well as even at Wipro Technologies, I have seen this where lot of students who have been trained and worked on the projects, they used to come confidently to the right HR team saying that I am already been trained on this particular trade of the job. Okay, why don't you put me into that job? And always the HRs have done that for the students. So I believe uh, as a industry, we are ready to assist you. And probably now the ownership is with right, our academic network like Dayanand Sagar, and definitely even students, okay, right, among us, okay, that you make your career choices very early in your engineering, so that instead of you completing a graduation and leaving your career options to the industry, you can define the career option yourself, so that you can really go and enjoy your career in the industry. So this is what we are offering from our organization, okay, along with our partner Excel VLSI Technologies, right, and we hope that, right, these initiatives will definitely help, right, the skill deficiency which our country is facing, and definitely by joining our hands, we can address those things. So with that note, I'll stop at my end. If you have any questions, you are you are, you can share that with us.
Thank you, sir, for your valuable information regarding VLSI internships, projects, and career builder programs. Uh, Dear students, if you have any questions, you can ask now. Nikhil, Kaushik, you
So
can ask.
now in the fifth sem, we actually have the Verilog subject. Hello.
Yeah, we can hear you. Yeah, you can ask.
Nikhil, go ahead, please.
Sir, in the fifth sem, now we actually have the Verilog subject along with the labs. So we are exposed to the basics of it and the programs like flip-flops, etc. So after learning this, what could be the further learnings so that we can go into this industry?
Okay, so let me take you through one of my previous slide, okay, which basically shows, okay, because of the time constraint, I didn't ran through those things for all of you. So Nikhil, you are specifically asking that I'm learning my digital basics in my in your third year, okay, or second year, and from here, what are the options in front of you? That is what you want to know. Am I right?
Yes, sir.
Okay, so you take a look at it. This is the skill index, which is for the physical design engineer. Okay, right, where, right, if in case if you are an engineering graduate who is really passionate about the VLSI or core industry, but you are starting your journey on the digital electronics. In the higher semesters, Nikhil, you will go through ASIC design, right? You also learn digital system design using Verilog HDL. And definitely in that process, you will also get exposure to Linux and some scripting knowledge also. And you also learn some timing analysis concepts. So in fact, those are the skills what the industry requires for an engineer to be ready for the physical design and verification job role. But the engineering curriculum of our academics basically gives you the conceptual foundation, but it requires the practice also. So by exposing yourself into the concepts of uh, scripting like TCL and Perl scripting and Linux, and then timing analysis concepts and physical design and verification, right? Through add-on courses or else internship programs, right? You can get yourself right ready for the physical design and verification engineering job profile. That is one option. Second is that you may say that I'm learning the digital electronics basics. Now In the future, my interests may go towards the analog CMOS concepts. Yes, so you can even build your career for analog circuit and layout also as a design engineer, where once again the knowledge of analog IC design, right, and layout concepts, scripting and Linux for the VLSI engineers, and analog layout design concepts and analog and mixed signal design. That is another option for the engineers, right, who are not really program savvy, but they are more savvy about the CMOS concepts and as well as the core physics of the electronics. Okay, for them, this is the job role option. And one more interesting job role is the verification engineering. For example, if you are an engineer, Nikhil, who is really passionate about digital electronics, but at the same time you are logic oriented guy and you like programming, then basically the verification job profile is something, right, which you can choose upon. Okay, right, with fine tuning your skills on verification using Verilog based verification, system Verilog based verification, then UEM concepts through a phased learning approach in your higher semesters. In your probably fifth and sixth semester, you will learn C++. So you need to learn the concepts of system Verilog, and you need to work on at least a moderate complexity projects, okay, right, on system Verilog, and you need to get exposed to UEM concepts, and you need to work on some mini project or major project as a part of your learning. And once if you do that, by the time you enter into your final semester, you will be in a competent position that to choose a problem statement of either a memory controller or else an right IO interfaces, okay, concepts, where you can take that as a project in the final semester and do it and showcase that as a part of your right profile to the industry. Definitely that makes you ready for verification jobs. Okay, so this is how, irrespective of where you are, all of you as students, you choose, okay, right, whether you are programming savvy, right, and aiming for a job in VLSI and electronic system design industry, or else if you think that programming is something which is not your cup of tea, but you really enjoy your electronics concepts, okay, right, at the grassroots level with the passion for CMOS concepts and everything, then you can choose either right physical design and verification, or else you can choose right analog circuit and layout. So there are different job profiles which are available for all of you, in fact. So you can choose, and accordingly you can start building your learning plan.
Thank you.
Um, Thank you, sir. Nikhil, you can share your views on the webinar.
Yes, ma'am.
Yeah,
Am I audible?
yeah.
Yeah. Good afternoon, one and all. Myself, Nitin TM from 5th Sem. A very well structured and thoughtfully organized webinar. Thanks for our department. Well, Mr. Shivappa sir had a very thorough understanding of the topic, managed to break down hard topics into easy parts, and also very articulate in explaining. Thank you so much for that, sir. From this webinar, we got to know about VLSI industries, career opportunities in this industry, also design, front end, back end concept, and funding opportunity. In the demand for the VLSI designers is quite high in order to develop FPGA implementations, system on chip, and applications, specific integrated circuit also. With the Indian market scenario looking good, the scope of VLSI design professional is bound to grow, I think. And this industry is very growing. And well, we have advantage in this VLSI industry, as sir said, because we are learning Verilog in 5th sem, and also we are from electronics department. So we need to make use of that. And finally, thanks for our electronics department, our faculty, and mainly Mr. Shivappa sir for providing such a wonderful webinar for us. Thanks. Thank you so much. Yeah, ma'am.
Thank you. Nikhil, you want to give share views on the webinar? Nikhil Kaushik.
The webinar explained us the brief idea about how the actual VLSI industry works. Through the webinar, we were exposed to the detailed design flow, which involves going through making a chip right from the scratch. It also included the major advantage as well as the disadvantage that leads when we use FPGAs or ASICs in common. And the webinar also included the various career paths that we could have taken to enter into the field of VLSI that many of us didn't know actually, and the projects that we had to take up to go into the field. It also included the full custom design flow and the way in which it was different and advantageous when compared to the digital design flow as well. It also explained the various challenges that are present to get into the industry and the lack of skills that we have and the various opportunities that they provide to increase our skill set. So thank you very much for this wonderful webinar organized. Thank you.
Thank you, Nikhil. Any questions, Ananya?
Yes, ma'am.
Yeah.
Ma'am, like sir told about those industrial training or short-term programs and career building that is respective for 6 weeks, 3 days, or 4 months. So, like, if like I am in fifth sem and like yeah, like he told, if it would be better if we have started from second year. But now, if I want to target those trainings, so can we like with college we can have those trainings now, or like so that we would have a better idea which field we can choose or get trained.
Damodar sir, is he there?
Okay, so let me address that. Damodar, are you there? Okay, so NTPL, right, they reach out to all engineering colleges and they are organizing internship programs. And in fact, since last how many months? So about 6 to 7 months, we started in the month of March. More than 2,000 people have taken up our internship programs. And this usually we have divided these skill wise. For example, Verilog internship, design verification using Verilog internship, 1 month program. You will have 10 to 12 sessions every day, not every day, weekly 2 to 3 sessions, and it will be for 2 hours. And you will also be enabled with the tools, and you can do hands-on. We will be giving lab exercises. There will also be person from NTPL supporting you on tool side and also helping technically. And we will also be giving one project assignment, and then as part of the internship, you will do a project and then submit to us. There'll be assessments as well. So we have programs in Verilog, System Verilog, and physical design. Right? Physical design would include synthesis, STA, and physical design complete part. So that way, in fact, now System Verilog and PD are going on, and we have also rolled out Career Builder program. So for all these, you visit ntpl.com website or even our website. We have briefed there, and then you can write to us, or you can call us, and we will be giving you information when we will be starting our next internship program. And till you complete your 8th semester, you are open to take up any of our internship program. Okay, so it's not mandatory, and we will be running these programs almost every 3 months. We will be running, right? So that way, if you are very much good at Verilog, you can directly take up System Verilog. Otherwise, you start from Verilog, right? So so that way you can choose. Visit our website for further information, and then you can reach out to us.
Thank you, sir.
Yeah, thank you. Ananya, I think you can take up the internships after the college hours, and they provide in the evening also. Okay.
Okay, ma'am.
Okay. Now I request Professor Mansa to give vote of thanks.
Yeah, just before that, I just wanted to have one comment here. The talk is titled with funding opportunities. I have not mentioned anything about the funding part. My apologies. And of course, I covered only the technical part of it and industry overview and what are the trainings we provide and those kind of things. Sorry from my end, actually.
Good afternoon to one and all. On the behalf of ECE Department DSC, I, Manasar, Assistant Professor, consider it a great privilege to propose a vote of thanks. I would like to begin with a quote by Larry Rusak. Knowledge is in groups, not individuals. Our special thanks to today's speaker, Mr. Shivappa, for enlightening us in the area of VLSI and making us to understand about VLSI industry overview, semiconductor growth in India, VLSI ecosystems and employment opportunities, challenges in power, performance, and area. Most importantly, about ASIC design flow, test bench in Verilog, and so on. So I'm very sure that your remarks have triggered new insights in current research to our dear students. Thank you very much, sir, for sparing your valuable time with us. Our special thanks to Mr. Damodar Shambashivam, Business Director in N-Tuple Technologies. Thank you, sir, for lending a hand to our webinar. The information given by you will definitely provide ideas and guide our students to choose their career in VLSI. Thanks a lot, sir. I would like to extend our special thanks to management for giving this opportunity. I would like to thank our beloved principal, Dr. C.S. Prakash, for his constant support. I would like to thank our dear HODs, Dr. T.C. Manjunath and Professor Dr. Dinesh sir, for encouraging us always. I must mention deep sense of appreciation to Professor Madhura R and Professor Navya for successfully organization of this webinar. Thank you.
Yeah, thank you all.
Yeah. Thank you, students. I think we can end up the session by now. One more thing I want to tell, we will be sending the feedback link for all the students. You just fill up and submit it. Okay. 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 Thank you. We'll end up the session. Thank you, sir.